All right, good morning. It is great to see you guys this morning. Today we are going to be talking about vectors and scalars, and specifically about vectors and how we can use them in physics. So first of all, the first question is, what is a vector? A vector is a quantity that is described by its magnitude and its direction. So it's a quantity that has both magnitude and direction. And that kind of brings up the question, what is magnitude? Does anyone know? Yes. Okay. It's actually it's the amount, but without regard to sign. So I guess we could say the absolute value. I usually just say it's the amount of something, but yeah, it's the absolute value of a quantity. So it's the amount and then a direction also. So the vector is a quantity that has an amount and a direction, and it can be represented with an arrow. Represent. Okay, and we can represent it with an arrow. For example, if I drew this and labeled it as having a quantity of 5, and I just made that number up. I didn't make up any units. I just said, hey, I've got something that has an amount of 5 units, and its direction is which way? To the right. Good. Um, and then I could also have another one that might be 10 to the left. And what you'll notice is that these are proportional, meaning that the 10 is twice as large as the 5. So we like to draw them that way. We like to draw them proportionally. We are not always able to, because sometimes we get really big numbers and we can't represent those on the paper well. But the vectors should be drawn proportionally, meaning that the length represents the magnitude. So 5 to the right, and again, if we called right positive, then that would be like a +5. If we called left negative, this would be like a -10. So we can also represent the amount and the direction just with just signs and numbers. Now, so that tells us what a vector is, something that has a magnitude and a direction. And I used another word also. I said the word scalar. Okay. Does anyone know what a scalar is? S-C-A-L-A-R, scalar. It's also a quantity, but it's a quantity that only has a magnitude. That is, it only has an amount. It only has a size. It does not have a direction. It's a quantity with no direction, like so many people in life. Right. So let's think of these now in terms of some examples. Um, what would be what would be a vector quantity? That is something that has an amount and a direction. What's something that we've talked about that has amount and direction? Velocity, excellent. So velocity, force, We haven't talked about force yet, but it has an amount and a direction. Acceleration, displacement, etc. So there are lots of vector quantities, and those vector quantities can be represented with arrows. Scalar quantities, on the other hand, don't get represented by arrows. They just get represented with a number, just with an amount. Can anyone think of an example of a scalar? Something that's fully described just by a number. Okay, area. What else? Time, excellent. Distance, speed, mass, temperature, and so on. Yeah, it's things that we can measure, but that don't necessarily have a direction. Like no one says, "Hey, I'm going to be going 14 seconds to the left." Or if they do, that's a little bit weird. Um, or how much mass does that object have? Oh, it has a mass of 3.2 kilograms. To the northeast. No, mass doesn't have a direction. So these are things that don't have a direction associated with their measurement, whereas all of our vectors do. Questions about that so far? All right. Um, Vectors, I want to talk about a couple of properties and how we can use vectors. I'm going to clear the screen for us. Vectors can be combined or added together, and they can also be moved around the page. So let's list those two properties separately. Let's see, my V didn't exactly form correctly. Vectors can be moved around the page as long as you do not change their amount or direction. So let's just say that I have a nifty little green arrow right down here, and that I really need for some reason to have it over here. Well, if I take it and just grab it and slide it, I can slide it all over the page, and that's a perfectly legitimate thing to do as long as I don't change its amount or its direction. Now, if I took that and said, "Oh, okay, hey, I need to move it over here, so I'm just going to redraw it, and I'm going to redraw it like that." That would not work because you notice that it's about the same length, but it is not at all the same direction. And so these two vectors are not equivalent. Okay, they are not the same. In order for a vector to be the same, you have to maintain its amount and its direction. Okay? How much and where to. Questions about that so far? All right. So vectors can be moved around as long as we don't change their amount or their direction. There we go. All right, and I'll just leave that guy there for now. Let's see. The other thing that I want to talk about is that vectors can be combined. Let's see, let's write this piece of information right here. Vectors can be added together or combined together. And so the question becomes, well, gosh, how do I add two vectors together, or how do I combine them together? Vectors are always combined head to tail. And we'll talk about what that means in just a second. Vectors are always combined head to tail. That is, the arrowhead of one is placed against the tail of another. The arrowhead of one vector is placed onto the tail of the next vector. So the arrowhead of one vector is placed onto the tail of the next vector. So if I wanted to, let's just say that I have another vector down here that I'd like to, and I'd like to combine my kind of pink purple vector with my green vector. And so what I'm going to do is I'm going to take my pink purple vector and I'm going to move it until, whoop, who knew that that would cover up that way. All right. Um, hmm. So I'm going to have to, let's see, do something slightly different. Yep, can't grab that. All right. And so I'm going to take the green one, and remember I can slide vectors around as long as they're not on, as long as I don't change their magnitude or direction. And I'm just going to slide it up to where the head of the green vector is against the tail of the pink purple vector. And so I have now added those two together. Now what has to happen is we have to sketch in the resultant, or the overall result. Let's see. So vectors are combined head to tail. That's how we add them. The arrowhead of one vector is placed against the tail of the next. And then the overall result, which is called the resultant, uncreatively enough. So the overall result is sketched in from the start of the very first vector from the start of the first vector to the end of the last vector. All right. So here's what I want us to understand with this idea is that while vectors are added head to tail, just like this, the resultant is sketched in from start to finish. And so that's going to be from here to here. And so that's my resultant, which I'll just label R. So the sum of the green and the pink purple vectors is the black dashed vector. What questions do we have about that? So that is how vectors are added. Two other things that I will mention. Number one, the order does not matter. Remember that addition is we have a commutative property which states that the order of addition does not matter. The order of the addition does not matter. You could add the green to the pink purple or the pink purple to the green, and either way you would get the same result. Because addition is commutative. 3 plus 5 is the same as 5 plus 3. We still end up with 8 either way. So, okay, take a look at this dashed black vector. Okay, and I want you to imagine what if I moved my pink purple vector down here? I would still then go from start to finish like that, and it would be the same. All right. So, so that is that the order of the addition does not matter, and you can add as many as you need to. Add up as many as needed. All right. So that talks to us about our about adding vectors head to tail, sketching our result from start to finish, and then adding and the order not mattering since addition is commutative. All right, let's clear the board. Oh, just kidding. There we go. Oh my goodness. I'm struggling this morning. Clearly, more coffee is needed. Everyone take just a moment and have a sip of your coffee. All right, great. Now we are ready to press on with the next idea about vectors. Um, now, now we are going to take something we just learned and do it in reverse. All right. So, since vectors can be since vectors can be added to produce a resultant, one could also take a resultant you can also take a resultant or any vector and break it into smaller parts. And here's what I'm saying with that is, just as I could take this vector and add it to that vector to get an overall result of that black dashed line, I could also take let's just say I could also take this one and break it down into two parts or more if I needed to. And what I want you to see is that just like here, I added them head to tail and drew my resultant start to finish. Here, I had a vector that I wanted to be my resultant, and I said, hey, what's that made of? And I said, it's made up of this much x and this much y. This vector goes down and right, which means it's made up of a rightward and a downward component. And just as I can add 3 plus 5 to get 8, I could also take 8 and represent it as 3 plus 5. So just as I can combine vectors to get a resultant, I can take a resultant and break it into parts or components. All right? And that is going to be extremely useful, particularly if we have an angled vector and we'd like to break it into its x and y parts. In other words, let's just say that I have this orange vector over here. And then I take that orange vector and I break it into, and this orange vector goes upward and rightward. And I say, you know what? How much up? How much right? And so I'm going to start at the very beginning of it, and I'm going to sketch in a rightward component, and then head to tail with that, I'm going to sketch in an upward component. And so I can see that this overall vector, let's not call it R this time, let's just call it vector, let's call it vector Q. Everybody loves vector Q. And so then I'm going to say, you know what? It goes in the X dimension this far, it goes in the Y dimension that far. And so QX plus QY actually make up vector Q, which means it's true the other way also. I can take Q and break it down into X and Y. And I can hear you wondering, Mr. Willis, why would I ever want to do that? Why would I want to take one nice, neat vector and break it into two parts? And the reason is because we might want to know how much of something is acting in the X and how much of something is acting in the Y. When we break a vector down, we are almost always going to break it into X and Y pieces. And that does two things for us. It lets us use, it creates a 90-degree triangle, which lets us use two math ideas that are going to be extremely, extremely important to us. What's one of them? Yes, the Pythagorean theorem. Okay, the idea that a squared plus b squared equals c squared. And so we can use, since we have a right angle, we can use the Pythagorean theorem to find values of one side if we know the other two. And the other functions, which may not be immediately apparent, are that with a right triangle, we can use sine, cosine, and tangent. All right, where sine, of course, is equal to the ratio of the opposite side divided by the hypotenuse. Cosine is equal to the adjacent side divided by the hypotenuse, and tangent is equal to the opposite side divided by the adjacent side. All right, and so the whole point of wanting to be able to break up vectors into components is in order to get an x and a y part, which we can then perform some calculations on in order to find maybe a missing value. And that's going to be all for this video. We'll talk more about our trig functions and our Pythagorean theorem in our next episode. All right, thanks for watching. Bye-bye.